Hello everyone, my name is Vipul Popat and I'm presenting the CA688I Assignment 2, the race towards a better consensus mechanism, where we are and where are we heading. I'll just give you some kind of an introduction to start with. Ledgers are using for decades in written form in this world, then slowly shifted from written to digital form and are kept in databases in different forms. Digitization allowed the world to make a global economy. This way of keeping information across global network is called decentralized ledgers. Blockchain is the technology for keeping data in a decentralized way. Blockchain is sometimes called decentralized ledger with timestamp. Audit has become so easy in blockchain because we can trace every information back and through at the time of their creation. Mostly, we have four types of blockchains available: public permissionless blockchain, public permission blockchain, private permissionless, and private permission blockchain. Beside the type of blockchain network, every blockchain network has become or has some kind of a consensus mechanism for block creation and finalization purpose. Because there is no central authority, the decision of block creation has being taken by some already defined rules in the network that every node must follow. By consensus algorithm, the blockchain is claimed to have solved the problem of Byzantine's generals problems and double spending in cryptocurrency. Consensus is core concept in distributed systems and not restricted to blockchain. It applies to scenarios in which multiple processes or nodes have to maintain a common state of data item. Permissionless and permission blockchains are two major types of blockchains. Consensus is still important to achieve in that case as nodes are not trustworthy. In general, consensus is worth to consider where the nodes of the network are faulty or they communicate in an unreliable way. Consensus is achieved in distributed systems with regardless of failures. Further, while defining consensus system communication models such as synchronous or asynchronous is also considered relevant. There are various categories of failures: crash failure, transient failure, omission failure, security failure, software failure, Byzantine failure, temporal failure, and environment perturbations. Consensus problem is difficult to be solved in asynchronous networks. To cater this, some randomized consensus solutions are proposed that relax three mandatory problems of Byzantine consensus agreement, termination, and validity. With rapid evolution of blockchain technologies, the demand for higher level of quality of services by blockchain-based applications presents more critical challenges in designing blockchain protocols. Particularly, the performance of blockchain networks significantly relies on the performance of the adopted consensus mechanisms. Example, in terms of data consistency, speed of consensus, finality, robustness to arbitrarily behaving nodes, and network scalability. Compared with the classical Byzantine consensus protocols, allowing very limited network scalability in distributed systems, most of the existing consensus protocols in open access blockchain networks, example Bitcoin, guarantee better network scalability at the cost of limited processing throughput. Also, to achieve decentralized consensus amongst poorly synchronized trustless nodes, a number of these protocols incur high consumption of physical resources, for example, computing power. Moreover, to ensure a high probability of consensus finality, the protocols may also impose high latency for transaction confirmation. Out of such concerns, a large volume of research has been conducted with the aim of improving the performance of the open access blockchain consensus protocols in specific aspects. I would take you through a few objectives of the consensus mechanisms, which are unified agreement, aligned to economic incentive, fair and equitable distributions, prevention of double spending, and not but and last but not the least, fault tolerance. Most common consensus mechanisms on blockchain platform are proof of work and proof of stake, which have indirectly influenced many other types of consensus methods. Proof of work is a mechanism also known as mining, and the miners are known as nodes. Miners solve complicated mathematical puzzles that require extensive computational power. After solving the mathematical puzzles, a miner receives a block as reward if they are the one first to find the solution. Additionally, the puzzles can also be solved with trial and error. Hence, the miners require an increasing amount of computational power for finding solutions quickly. Proof of stake is a mechanism which uses randomized process to figure out who gets a chance to produce the next block. Blockchain users that lock up their tokens for a certain time for becoming a validator. After becoming a validator, users are able to produce blocks. Validators usually get rewarded for their work with all or part of transaction fees of all the transactions carried out in the block they created. The third most common consensus mechanism is delegated proof of stake, which allows users to spend their coins to vote for various delegates. Once these delegates have been elected, they are able to make critical decisions that apply to the whole network. For instance, the elected delegates can set protocol rules or validate transactions. This mechanism has helped to ensure the blockchain protocol remains sustainable and scalable. And last but not least is the practical Byzantine fault tolerance, which is the ability of a distributed computer network to correctly reach a sufficient consensus despite malicious nodes in the system failing or sending out incorrect information. The goal of PBFT is to protect against catastrophic system failures by reducing the influence of these malicious nodes. PBFT is derived from the Byzantine generals problem, which is a long-term computer term, which is a computer science term for situation where involved parties must agree on a single strategy to avoid a complete failure. However, it assumes some of the involved parties might be corrupt or otherwise unreliable. Now we compare the most common consensus mechanisms on various features, which is energy consumption, transactions per second, transaction fees, structured, tokens required, security threat, and others. As we see from the comparison table, proof of work is highest at the energy consumption, and PBFT is the most efficient in terms of transactions per second. The transaction fees in proof of work is the highest and PBFT is the lowest. As we see that the proof of work and proof of stake prove to be the most decentralized of the blockchains, and security threat in proof of work is not that much because there is high concentration of power. With respect to delegated proof of stake, there is a possibility of candidate cheating, and in PBFT, there is definitely a chance of the denial of service attacks. Further to the four consensus mechanisms which we spoke about earlier, I'll take you through a few evolving consensus mechanisms on the blockchain platform as shown in the figure. I would elaborate on a few of them as we speak, namely proof of authority, which is a modified version of proof of stake, where it identifies or validators in the network are at stake. The identity is the correspondence between validators' personal identification and their official documentation to help verify their identity. These validators stake their reputation on the network. Also, the number of validators are fairly small, maybe 25 or less, so it is more of a centralized mechanism rather than a decentralized. Another one is proof of activity. This mechanism is a combination of proof of work and proof of stake. Here, the miners try to find the solution to a puzzle and claim their reward. However, the blocks created in this mechanism are simple templates with mining reward addresses and header information. Once the selected validator signs a new block, it becomes the part of the network. In case the block stays unsigned by some validators, it gets discarded and the new block is utilized. The network fees generated in the process are distributed between the winning miner and the validators. Decred is the most well-known cryptocurrency that uses proof of activity. Proof of space-time is another implementation of proof of storage in which server can publish proof of storage where verifiers can refer and investigate whether the transmitted data was being stored during a particular period of time. Proof of space-time eliminates submission of proofs to the blockchain that correspondingly retrieves or prevents the frequent interactions of the verifier and the power. An example of proof of space-time is Filecoin. Proof of devotion. This is an integrated proof of stake and proof of identity in which nodes with the greatest impact on the network's ecology are given permission for the blockchain generation, for the block generation. Block proposer will be chosen using participants from a divisor of validator sets, which are referred to as dynasties in round of BFT voting. This process facilitates determining the legitimacy of the proposed block. Example, Nebula. Least proof of stake is an algorithm that was proposed by Waves. Waves created the custom token in a decentralized blockchain and it consumes less amount of power. Least proof of stake creates a centralized environment inside a decentralized platform and allows the small holders to get the chance of staking. In this, coin holder can get benefit by leasing the coins. Proof of importance. Proof of importance was introduced by NEN. Proof of importance is the advanced proof of stake in which nodes are eligible to add blocks to the network. Is dependent on the score in proportion to the currency vest by node into the network or node's importance scales determines. Proof of importance algorithm is formed on an aggregate the nodes by analyze the transaction graph. In this on hash basis of hash calculation, the most important nodes will be assigned priority. I will go through the key takeaways. The blockchain with proof of work consensus was first developed to solve the cryptocurrency double spending problem and the Byzantine fault problem. The proof of work consensus solved the problem very effectively, but due to its high computation and specialized hardware need, a lot of questions from the society have been raised on the proof of work consensus. To solve the limitations of proof of work, a lot of other consensuses have been proposed in literature as an alternative solution of proof of work. Despite having similar goals, various blockchain consensus mechanisms ensure consensus with a varying approach. A single reliable consensus mechanism does not exist yet, but existing ones have evolved over time to meet the needs of blockchain technology. Additionally, predicting the type of blockchain consensus mechanism that will be popular and useful in the long run can be increasingly complex as the underlying technology is fairly new. Hence, the business leaders who wish to introduce blockchain technology in their organization must be well informed about the various blockchain consensus mechanisms. The blockchain technology has a great future in many areas, not only in the field of cryptocurrencies, but in also in various other ICT applications from various dimensions like security and privacy of data. Consensus algorithms have promised stable operation in this technology. Its consistent consensus algorithm nodes agree on a certain value and transaction to the consensus protocol. The key parameters that need to be evaluated for comparison covers both security, performance. Apart from these, a number of other aspects which are also important to be considered. Network topology, that is the fully connected graph, transaction rate, consistency achieved by consensus solution, concurrency check, transaction verification speed, and complexity of rounds. Proof of work proves its usefulness to solve the problem of double spending, but has issues around energy inefficiency and hash rate consolidation. Proof of stake seems to be the base for all the other algorithms and mechanisms which have evolved over a period of time, but has its own issues around nothing at stake and gold finger attacks. I'll also elaborate a few takeaways in terms of Cardano and Polkadot, starting with Cardano. The most recent example of POS blockchain, which seems to be fully decentralized and scalable, is Cardano. POS blockchain simply cycle through the block producers when it comes to minting a new block in a round robin type selection. Instead, POS blockchains, some POS blockchains randomly elect leaders for each round or slot who are called the slot leaders in Cardano. The most critical algorithmic component is the slot leader election procedure, which determines the subset of participants with the authority to add a new block to the blockchain during each round. Slot leaders are chosen according to the stake in the protocol or the protocol tokens which they control relative to the rest of the staking participants. Cardano now operates on Oboros Krauss, a POS protocol that is first to be provably secure against adaptive attackers and scalable in true practical sense. The design of staking pools and delegation of Cardano ensures that protocol has much greater capacity for decentralization, encouraging the creation of thousands of stake pools and a theoretically unlimited number of delegates. In future, the nodes or the leaders could be elected based on a combination of different consensus mechanisms rather than just relying on one, which gives a flexibility for node participants to participate in the block minting process and also foster decentralization and democratization. I would go with the Polkadot parachains, which are heterogeneous blockchains that are connected to Polkadot blockchain. They are interoperable with Polkadot network and other parachains. A parachain runs parallel to the Polkadot relay chain, and that is how it derived the name parachain. Here, the idea of running parallel to a relay chain is indicative of parallel nature of parachain, which enables it to parallelize transaction processing with the Polkadot system and achieve its scalability. That is one benefit of becoming a Polkadot parachain. The other prime advantages of parachain is that it can interact or communicate with other parachains of Polkadot. Also, it shares the security of the entire network. There is so much buzz around parachains because by design, they share the Polkadot cross-chain composability and interoperability. Because of this, they can send or receive any type of data or asset with other parachains. Thereby, parachains are capable of supporting a host of new use cases and applications. course, they also share and benefit from security, scalability, and governance of Polkadot. In the end, all of these mechanisms have similar goal, that is to have consensus in a decentralized network. However, even after having a shared goal, these mechanisms differ in the way to approach reaching consensus. While the ideal consensus doesn't exist yet, it's fascinating and moving to see how these consensus mechanisms have developed and adjusted over the long run to changing requirements of protocol like this, and it will unquestionably be exciting to observe groundbreaking ideas materialize. It is important to wisely pick the one according to the business network necessity, as the blockchain networks can't properly function without the consensus algorithms to confirm every transaction that is being committed. These are the references I have used in order to derive the content for this presentation. Thanks and bye, everyone.